Welcome to the deep dive. Today we're tackling something really important for where AI is heading, making these huge, large language models run faster.
And more efficiently, especially, when you feed them enormous amounts of text, like long documents.
Exactly. We've got this stack of material you provided, notes, study guides, quiz answers, briefings, even parts of our research paper about something called DSLA-Serve.
That's the one. So our job today is to unpack all of this.
Right.
We want to get past the jargon, figure out the real problems they're seeing, and, most importantly, understand the innovative technical ideas they're proposing, especially for LLM serving, which is, super dynamic in the real world.
Definitely. Because anyone who's tried using an LLM on, say, a long report or a big chunk of code knows it slows down a lot.
Yeah, it's computationally intense, and it eats up memory like you wouldn't believe.
So that's our starting point.
Yeah.
That fundamental bottleneck.
And your sources are crystal clear on where that bottleneck is. It's right at the heart of the transformer architecture.
The self-attention mechanism.
Bingo. That's the core of the issue.
Okay, let's dig into that. Why is self-attention such a performance hog, particularly for these long inputs?
Well, it's how it's designed. Fundamentally, it needs to look at every single word or token in the input.
Okay.
And compare it to every other token. So if your input has length t, the computation scales quadratically.
OT.
Exactly. OT, so double the input length.
You quadruple the work.
Precisely. It just explodes for the kind of long context we really want these models to handle. It gets slow, really slow.
Brutal. And it's not just the computation time, right? There's a memory cost, too.
Absolutely, a huge one. During inference, especially when the model's actually generating text, the decoding part, it stores intermediate results from these attention calculations.
And the KV cache.
Yep, the key value cache. And its size grows linearly with the sequence length and the number of layers in the model.
So long sequences, deep models, massive cache.
You got it. It can take up enormous amounts of GPU memory, which is often the scarcest resource.
Okay, so quadratic compute, linear memory growth with the cache. Makes sense that people looked for alternatives, like linear attention, OT, complexity.
Correct. That's been a major research direction. Linear attention models usually maintain a kind of fixed size hidden state that summarizes what they've seen so far.
So they process token by token linearly.
Which is much faster computationally.
OT.
But there's a catch with the standard single-state linear attention models.
What's the catch?
It's something called recency bias.
Recency bias, meaning they pay too much attention to the newest stuff and forget the beginning.
Pretty much. That single state has a limited capacity. It struggles to compress and hold on to important information from way back in a long sequence.
Okay.
Your figure 1 actually shows this quite nicely. You see a standard transformer like Llama 2. Its attention is spread out, looking back.
Right.
Then you look at GLA, gated linear attention, which is the single-state model.
And it's all focused right at the end.
Exactly. Heavy focus on the most recent tokens. And that really hurts performance on tasks where you need the whole picture, like summarizing a long text or answering complex questions about it.
So just ripping out all the self-attention and putting in basic linear attention isn't the answer either.
Not really, especially because real-world LLM serving isn't neat and tidy. It's dynamic.
You mean the load isn't constant?
Right. You get bursts of long queries, memory usage spikes, maybe one server gets hammered while another is idle. Your figure 2 illustrates this with those memory spikes and imbalances they saw in real traces.
So static models, all transformer, all linear, even fixed hybrids, they just can't cope well with that variability.
It's tough. You either over-provision resources like crazy, which is expensive, or you risk performance tanking when things get busy. There's a real need for adaptability, something dynamic.
Okay, that sets things up perfectly for the first big technical idea in these sources. Dual-state linear attention, DSLA. Sounds like it's built to fight that recency bias.
It is. That's its core purpose. And the key innovation, like the name says, is using 2 specialized hidden states per layer. Not just one like GLA or other earlier linear attention models.
2 states. Okay, what do they do? Are they different?
Yes, specialized roles. The paper says one state, let's call it S1, focuses on preserving historical context. It tries to remember the stuff from earlier on.
Like a long-term memory.
Kind of, yeah.
But
And the other state, S2, is for tracking recency. It focuses more on the immediate past.
short-term memory. Figure 5 shows how they specialize, right?
Exactly. It visualizes how they learn to pay attention to different parts of the input history.
So having both gives the model more bandwidth. more capacity to store those mid or far-range tokens.
That's the idea. It creates a richer representation of the input history. And critically, each state still updates linearly. You keep that O2 efficiency. But together, they can mimic full self-attention's ability to handle long-range dependencies much better than a single state ever could.
That's clever. Just doubling the state gives you that much more power. But how do they combine the information from these two states? Is it just fixed?
No, and that's another cool innovation. The learnable coefficient, gamma.
Learnable, so it's not preset.
Right. Each layer learns its own specific gamma value. And this gamma acts like a blending knob, controlling how much influence the historical state, S1, and the recency state, S2, have on the layer's final output. Equations 5 and 6 describe this blending.
Okay, so each layer figures out its own preferred balance.
Yeah, and figure 6 is fascinating here. It shows the learned gamma values vary a lot across different layers.
Suggesting some layers prioritize history, others prioritize recency.
Exactly. Based on whatever their role is in the network. It's like the model learns where different types of memory are most useful.
That's really elegant. But wait, how do you make sure the two states actually learn different things? Couldn't they just end up learning the same patterns?
Good question. They use a specific training technique for that. Contrastive regularization. They call it Lobosetta.
A penalty during training.
Basically, yes. It's an extra term added to the loss function. Equations 9 and 10 detail it. But the core idea is to push the gating functions, the parts that control what information flows into S1 and S2, to be dissimilar.
So it actively encourages them to specialize.
Precisely. It forces them apart, computationally speaking, reinforcing their distinct roles.
And do they check if 2 states is the right number? Not 1, not 3.
They did. There's an ablation study, Table 5. It shows going from 1 state to 2 gives a big performance jump.
Validating the core idea.
Right. And going beyond 2 states, the gains started diminishing. So 2 seems to be a sweet spot, enough capacity improvement without adding too much extra complexity.
Okay, so DSLA is the smarter, dual-state linear attention block. But the real deployment magic seems to come from the framework using it. DSLA-Serve, the adaptive part.
Exactly. DSLA-Serve is about using DSLA not just as a replacement, but as a tool for dynamic, on-the-fly optimization during inference.
So it can swap layers in and out based on what's happening right now.
That's the core concept. It dynamically converts standard transformer layers into their pre-trained DSLA equivalents based on real-time conditions like memory load or how long the input query is. Figure 8 gives a nice overview.
Adaptive. Okay, how does it decide which layers to swap and when?
It's a 2-stage process, really. First, before deployment, they do what they call layer ranking.
Offline analysis.
Right. They take each transformer layer, train a DSLA version of it, that's distillation. Then they rank all the layers based on how sensitive they are to being replaced.
Sensitive meaning how much performance drops when you swap it.
Yeah, how much accuracy or perplexity changes. And they found a really neat way to estimate the sensitivity.
What's the metric?
Attention entropy. Equation 11. This is a key finding. Layers with lower attention entropy.
Meaning their attention is more focused, less spread out.
Exactly. Those layers turned out to be less sensitive to being replaced by a DSLA layer. Figure 7 shows this correlation. Lower entropy generally means a smaller performance hit when you convert.
So those low entropy layers are the first ones you'd want to convert if you need to save resources.
Precisely. They're the best candidates for efficiency gains with minimal accuracy loss.
Smart. Okay, so you have this ranked list based on entropy. Then, at runtime, what pulls the trigger?
That's the adaptive conversion logic. It kicks in when needed, say, GPU memory usage gets too high or a really long query comes in.
And it starts converting layers.
Starting with the least sensitive one from the ranked list, then the next least sensitive, and so on.
Until when? Does it just keep going?
No, it has stopping conditions. Either memory relief achieved, maybe GPU usage drops below some target threshold, or accuracy at risk.
Meaning converting the next layer might violate your performance target, your service level objective, or SLO.
Exactly. It stops before crossing that line. And it also smartly prioritizes converting layers for the longest queries first, because that's where you get the biggest bang for your buck in terms of memory and speed.
This whole dynamic approach feels much more practical for real-world serving than just having one fixed model. It lets you trade off speed and memory versus accuracy on the fly.
That's the goal. Intelligent resource management in response to actual conditions.
Now there's another crucial piece they mention. Chained fine-tuning. Sounds important for making this work without breaking things.
Oh, it's critical, absolutely vital for maintaining performance. The problem it solves is a potential mismatch.
A mismatch between training and inference.
Yeah. Imagine you train each DSLA layer, assuming all the other layers are still transformers. But then at inference time, DSLA-Serve decides to convert, say, 10 layers at once.
Those 10 DSLA layers might interact in ways they weren't specifically trained for together.
Exactly. That could lead to unexpected performance drops. Chained fine-tuning prevents this.
How does it work?
It's a sequential process laid out conceptually in Figure 3. They fine-tune the layers progressively in the exact same order they would be converted at inference time from least sensitive to most sensitive.
Walk me through that sequence again.
Okay. Step 1. Rank the layers by sensitivity using attention entropy. Step 2. Take the least sensitive layer. Convert only that one to DSLA. Freeze all the other layers as transformers. Fine-tune the whole model. Step 3. Once that's done, commit that first layer it stays DSLA permanently. Step 4. Move to the next least sensitive layer. Convert that one to DSLA, keeping the first one as DSLA, freeze the rest, and fine-tune again.
I see. So layer number 2 is fine-tuned knowing that layer number 1 is already DSLA.
Precisely. And layer 3 is fine-tuned knowing layers 1 and 2 are DSLA, and so on. You build up this family of progressively converted models.
So no matter what percentage of layers DSLA-Serve decides to convert at inference, 20%, 50%, whatever that specific combination has actually been trained together through this chained process.
Exactly. It ensures consistency and significantly reduces the accuracy drop you might otherwise see when you start mixing multiple converted layers. It makes the adaptive strategy robust.
That's a really clever solution to a potentially nasty problem.
Okay, so putting it all together, the DSLA block, the adaptive conversion logic, the chained fine-tuning, how did it actually perform? What are the results, the trade-offs, the limitations?
The results reported in the sources look pretty promising. They seem to strike a good balance between getting efficiency wins and keeping the accuracy solid.
Let's start with speed. How much faster is it?
They quote some pretty impressive numbers, like 2.3x faster inference than Llama 2.7b and 3.0x faster than Zamba 7b, which is already a hybrid model.
Wow.
For long prompts over 2,000 tokens, the initial processing step, the prefill, gets a significant speed up. That's shown in Figure 4.
Okay. And the generation part, the decoding.
That's arguably the bigger win. Because DSLA layers don't use the KV cache, the time it takes to generate each new token stays roughly constant, regardless of how long the sequence gets.
Unlike transformers, where the growing KV cache makes each new token progressively slower. Exactly. Figure 4 shows that clearly. Transformer latency per token increases linearly. DSLA's stays flat. That means much more predictable, stable generation speed for long outputs.
Constant latency per token. That's huge for user experience, especially in chat applications. What about memory?
Also a major plus. Swapping in DSLA layers just eliminates the KV cache for those layers.
Which saves a ton of memory, especially for long contexts.
Right. And they found an interesting side effect here too, related to those latency spikes we talked about earlier.
The unpredictable delays.
Yeah. Figure 12 shows how DSLA-Serve reduces those spikes. They trace the cause in transformers, often back to memory allocation, calls Kudamalek taking ages under pressure.
Because the KV cache was constantly growing and needing more memory allocated.
Seems like it. By getting rid of the KV cache for converted layers, DSLA reduces that memory pressure and avoids those allocation bottlenecks, so you get not just faster average speed, but smoother, more consistent latency too.
Faster and more predictable.
Nice.
Okay, the crucial question. Accuracy. Does swapping layers hurt performance on tasks?
The goal wasn't to beat the original transformer, but to maintain comparable performance while gaining efficiency, and the results suggest they largely achieved that.
On what kinds of tasks?
They show competitive results on long context stuff, question answering, summarization, code understanding tables 1 and 2. These are tasks where that recency bias could really bite, so DSLA seems to handle them well.
And standard benchmarks.
Holds up well on short context benchmarks too, shown in Table 3. And importantly, Table 4 shows significant gains in overall system performance, like throughput and latency in simulated real-world serving scenarios.
Does it work on different models or just the ones they tested heavily?
They mention it generalizes. Tables 6 and 8 show it working across different model sizes, like 7B and 1.5B, and different architectures like Llama and Phi.
Sounds very adaptable. Are there any downsides or practical hurdles?
They do point out a few things. One is memory overhead during deployment. To do the fast switching, you need to have both the original transformer weights and the distilled DSLA weights loaded for the convertible layers. That takes more resting memory.
Makes sense. You need both versions ready. Any way around that?
They suggest things like offloading the inactive weights to CPU memory or disk and prefetching them when needed since you know the conversion order in advance.
Okay, manageable.
What else? Accuracy does eventually start to degrade if you push the conversion too far. They mention things get noticeably worse past maybe 75% conversion.
But the adaptive logic is meant to prevent that, right? By stopping before the SLO is breached.
Exactly. The system manages that trade-off. They also note that using a better teacher model for the initial distillation step can improve the performance ceiling of the DSLA layers.
And what about that potential rebatching overhead if different requests need different layer types simultaneously?
Yeah, Figure 11 illustrates that. If you're running batches of requests and some need a layer as transformer while others need it as DSLA at the same time, you might have to split the batch, adding some scheduling complexity.
Is that a big deal in practice?
They argue it's usually not. The massive memory savings from ditching the KV cache, especially with long prompts, tends to dominate any overhead from rebatching. So the net effect on throughput is still positive, especially for the target use case.
So the benefits generally outweigh that potential cost.
That seems to be the finding from their experiments, yes.
Okay, this has been a fantastic deep dive. We've really unpacked the problem, the OT compute and KV cache memory issues with transformers for long contexts. We saw why basic linear attention struggles with a recency bias. And then we explored DSLA-Serve's innovations.
Right, with the dual-state linear attention itself, with its history and recency states and that learnable gamma blend.
The adaptive conversion strategy driven by attention entropy to rank layer sensitivity.
And that crucial chain fine-tuning technique to keep everything consistent during partial conversions.
The whole package seems to offer a really compelling way to get significant speed-ups and memory savings, especially for long inputs, without sacrificing too much accuracy because it adapts.
Exactly. It's flexible, it's efficient, and it seems technically sound. It addresses a very real pain point in deploying these massive models.
It really makes you think, doesn't it? If we can dynamically swap attention mechanisms based on need, what else could we swap? Could future models adapt other components, maybe different processing blocks or even different expert modules within the network, depending on the task or the available resources right at that moment?
That's a fascinating direction, isn't it? This idea of dynamically composing or configuring parts of a model at inference time based on the immediate context, the query, the latency requirements, the hardware constraints. It feels like DSLA-Serve is a concrete step towards that kind of truly adaptable, resource-aware AI. A glimpse of the future, maybe?
Definitely food for thought. Thanks for unpacking all that with us today.